This is the first lesson in E&M, Introduction to Charge and Coulomb's law. So we'll be discussing fundamental properties of charge, insulators and conductors, induced charge, as well as Coulomb's law. Fundamental properties of charge. So when we think of charge, it is important to think of it as the property of an object. Although sometimes we may refer to charge as the object itself, like right here, we can call this a positive charge. What we really mean is the object that has positive charge. Charge comes in two types. It can be either positive or negative. So if you look on the right, we have positive charge and negative charge. Those are the two types it comes in. Opposite charges will attract each other, like this positive right here attracting this negative, and you can see that by the force arrows pointing towards each other. And similar charges will repel each other. So a negative and a negative are going to repel each other this way and this way. And this positive and positive are going to repel each other in opposite directions. Now, the net charge of an object is the sum of the individual charges within it. So if we look down here, we'll see that this object right here, this circle, has 6 positive charges, 1, 2, 3, 4, 5, 6, and 6 negative charges, right? And so if we sum those charges by taking the 6 positive plus the 6 negative, we will get a net charge of 0. Likewise, if you come over here and you say, okay, now we have 6 positive charges but only 4 negative, we will take those 6 positive plus those 4 negative and get a net charge of plus 2. And then continuing once more, one last example, we have 6 positive charges but 9 negative charges. So we'll do 6 plus negative 9 equals negative 3. And that's our net charge, is negative 3. Now we say an object is neutral if the positive charge is equal to the negative charge. In this first example, we have 6 positive and 6 negative, which is going to equal 0, and so our object is neutral. It's not going to have any effect. Let's say we brought this neutral charged object next to this positively charged object. The positive and neutral object are not going to have any effect on each other. Same way, if we bring it near this negatively charged one, they will not have any effect on each other. However, if we were to bring this positive charge and this negative charge near each other, they are going to attract each other, similar to up here. And so, in any process, net charge is conserved, meaning charge cannot be created nor destroyed. It can be changed in the sense that you remove charge or you add charge, but you can never make a new charge in the universe. If you add charge, that charge had to come from somewhere else. If you remove charge, that charge had to come from somewhere else. Charge has the SI unit of coulombs, which is denoted by C, and 1 electron is approximately negative 1.602 times 10 to the negative 19 coulombs, so incredibly small. And that negative is there because electrons have negative charge on them. Let's move on to the next slide. We have insulators and conductors. We will get more in depth with insulators and conductors in later lessons. For right now, we just need some exposure to it. So conductors are able to transfer charge across 2 objects of differing charge, which is the formal definition, although that can be very confusing. Really, conductors have free electrons within their atomic structure, which allows electrons to move within them. So if we look over here, consider this copper cylinder to be a conductor. We have these mobile electrons that can move throughout it. And what this allows is for charge to be transferred in the sense that if we touch a positive charge right here, the negative charge will flow into the positive charge, because keep in mind, the negative is being attracted by the positive, and it will flow into that positive conductor with a positive charge. So the origin of this free electrons, you can look down here, comes from the atomic structure. If we look, the nuclei are locked in place. They cannot move, which means that our protons, which keep in mind have positive charge, our protons cannot move. However, some electrons are locked in structure, but some are not. These are, if you took a chemistry course, we'll call them as valence electrons. These valence electrons are able to move throughout the conductor structure, allowing them to be transferred from one conductor to another and just generally be affected by electric force, which we'll talk about in a second here. If I were to add a positive charge right here, these valence electrons would move to the left because the negative is attracted by the positive. However, these protons will not move. Protons in atomic structure can never move, which means you will never say that a positive charge was transferred. You will always say that a negative charge was transferred, And let's say you had something flowing from, you had a positive charge and a negative charge, and you touch them together and they neutralize each other. No positive charge went to the negative charge side. The negative charge went to the positive charge. That is a very important concept. Electrons move, protons do not. An insulator, on the other hand, does not have free electrons. So effectively looking at the same atomic structure, but there are no valence electrons that are free to move. Insulator cannot transfer charge in the same way a conductor can. So if we were to imagine that these valence electrons were not there, and then place a positive charge here, effectively nothing would happen. When we go more in depth about insulators and conductors, we will further discuss this topic. Semiconductors have properties that lie between insulators and conductors, so this could vary heavily, and there's a whole field of research into semiconductors, but they're somewhere in between. So let's talk about induced charge now. Charge by conduction occurs when a neutral conductor comes in contact with a charged conductor. So let's look right here. This is a neutral conductor. This is a charged conductor. The charged conductor will give some of its electrons to the neutral conductor until they have the same amount of charge. So when the neutral conductor comes in contact with the charged conductor, electrons, recall from conductors, electrons are free to move throughout the structure. And so since there are more electrons here, they want to get away from these other electrons. These electrons are repelling each other right now. And when you introduce this neutral charge, suddenly they have somewhere to go. And so they will balance out so that there's the minimum repulsion between electrons. Charge by induction occurs when a charged object goes near a conductor, causing the electrons within the conductor to be repelled or attracted based on the charge of the object, and it leads to an imbalance within the conductor. So if we look within this conductor here, we have a neutral conductor here, but a charged conductor here. We have this negative charge, which is going to not attract the positive charge, but rather repel the negative charge. Remember, the protons, meaning the positive charge, cannot move within the structure. So right here, what is really happening is this negative charge is repelling this negative charge, and the positive charges are staying in place. This kind of can be a confusing subject because the positive charge here is not due to an abundance of protons, but rather a lack of electrons neutralizing the protons' effects. So if we look here, these negative charges are repelling these negative charges, which is going to make more negative charge lie on this side. However, the protons do not move. There is a positive charge because there's no electrons neutralizing them. Last section for today, Coulomb's law. Coulomb's law provides the force between two charges. So the force is determined by K, which is Coulomb's constant, which is approximately 8.99 times 10 to the 9 newtons meters squared per coulomb squared, times Q1, which is the magnitude of one of the charges, times Q2, which is the magnitude of another charge, all divided by r squared, and r is the distance between the charges. So if we look up here, we have Q1 and Q2, and these are of the same sign, and if you recall, that means that they're going to repel each other. Similar charges repel, opposite charges attract. So we have two positive charges here, meaning they're going to push each other away. So we have F1, which is going to go towards the left, and F2, which is going to go towards the right. We can figure out the magnitude of these forces by plugging in Coulomb's law. It's important to note that these forces are going to be equal, because Coulomb's law incorporates both Q1 and Q2. The force F1 is going to be equal to the force F2, just with different direction. Same thing down here. Now our charges are opposite, which means they're going to attract. So our force F1 is going to go towards our negative Q2, and our force F2 is going to go towards our positive Q1. However, the magnitude of a force is still given by Coulomb's law. So force is a vector, which means we can find its magnitude in a particular direction by breaking down the force into its components. So let's ignore this charge right here, this positive Q1 in the bottom left, and this charge is positive Q2 in the top right. If we look at only this positive Q1 and this negative Q2, how are they going to interact with each other? Well, they're going to attract each other. They're opposite charges, so we're going to have our force from Q1 is going to be pointing towards Q2, and our force from Q2 is going to be pointing towards Q1. And so, because those have a direction that don't lie directly on the X or Y axes, we're going to have to use some trig, and we'll get to that when we go to the problem solving section.